Okay, we are going to be wrapping up section 12.2, the last section here in the book. We talked in the previous video about how if the data set for your scatter plot either has some type of curve to it, it's either a power model or an exponential model, we can perform a transformation in order to try to achieve a linear scatter plot so that we could then run a linear regression and then use that linear regression to make predictions. So it says here, suppose that a scatter plot shows some type of a curved relationship between the two quantitative variables x and y. How is it that we could decide whether that relationship is a power model or an exponential model? So that's kind of the question. How can we decipher which of the two models the original shape of the scatter plot is? Okay, so here's what we're going to do. We'll take a look at this example, and I'll demonstrate for you how to distinguish between whether the initial model is power or exponential. It says on July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier using a telescope at Caltech's Palomar Observatory in California. Originally named UB313, the potential planet is actually bigger than Pluto and has an average distance of about 9.5 billion miles from the Sun. For reference, Earth is about 93 million miles from the Sun. How could this new astronomical body, now called Eris, could this new astronomical body, now called Eris, be a new planet? Now, at the time of the discovery, there were 9 known planets in our solar system. Here are the data on the distance from the Sun and the period of revolutions of those planets. Note that the distance is measured in astronomical units, AU, and the number of Earth distances, that is the number of Earth distances that the object is from the Sun. Okay, how many of those distances that the Earth is from the Sun that planet would be? Okay. So here's our data. Okay, you can see each of the known planets that we have here. This is the distance that planet is from the Sun, okay, in astronomical units. And this is the period of revolution. So in other words, how many Earth years it takes for it to make one full revolution here. Okay. Other information that we have down here is you can see in this scatter plot right here on the left, you can see that the explanatory variable is the distance in astronomical units, that is the x, and our response variable is the period or the number of revolutions in Earth years. Okay. Now, what's in this box is pretty crucial. It says, if the relationship between x and y is a power model, then we would achieve linearity by either taking log of the explanatory, comma, log of the response, or natural log of each of them. Okay, so if the original scatter plot is a power model, when you transform the data by taking a logarithm of both the exponent or the explanatory variable and the response variable, that new scatter plot should appear linear. The other option is if the original scatter plot is actually exponential in nature, then you would achieve linearity by leaving the explanatory variable the same, but only taking log of the response variable or natural log of the response variable, either way. Okay, so it's not really until you perform both of these transformations that you kind of get a sense of what the original relationship really was between x and y. And so what you see pictured here below in these two scatter plots are each of these two transformations. Now I'm going to go ahead and write above the first one. This first one, you can see how we did not change our explanatory variable at all. So the distance in astronomical units is still our explanatory variable, but notice that the response variable here, we did the natural log of the period. Okay, that's the number of Earth years that it takes for one revolution. Okay, now you notice in the scatter plot, when we perform that transformation, there is still a very distinct curve happening here, even in this transformed data, which is an indication that maybe this transformation isn't the best fit. Okay, what we actually did here with that is we were checking to see if the original data set was actually exponential in nature, because we left the explanatory the same. We only did, I think in this case, we did the natural log of the response variable. So let's move over here to this one where we actually did the natural log of the explanatory variable and the natural log of the response variable. And you get a sense when you look at this, definitely feels like this transformed scatter plot is much more linear. Okay, this would be our test of seeing, does this appear, or is this showing us that the original scatter plot, we're talking about this scatter plot right here, is in fact more of a power model, okay, more of a power model than an exponential model. So let's come on down here and let's look at part A. Okay, part A says, explain why a power model would provide a more appropriate description of the relationship between the period of revolution, that's our explanatory, and the distance from the sun, than an exponential model. Okay? So we can see here that our answer to this, and I already have this typed here, is since the scatter plot of distance and natural log of the period clearly is curved, okay, that was this right here, that is showing that an exponential model is actually not appropriate. However, the scatter plot of natural log distance, natural log period, shows a linear form, indicating that a power model is more appropriate. Okay, just a little play on words here that I kind of use to sort of memorize these. You're performing, when you're checking to see if the original is a power model, you are transforming both the x and the y variable. It's like you're a little bit more powerful because you're sort of doing like a transformation to both of your variables, whereas if you're checking to see if it's exponential in nature, you're actually not transforming the x variable at all, you're only transforming the y variable. So power model, think like, oh, okay, more powerful because I'm actually doing log of both the x and the y. Okay, so there's our answer for part A. Let's jump over here to part B. It says, in part B, the mini-tab output from the linear regression analysis on the transformed data, we're talking about the one where we said the power model was more appropriate, is shown below. Give the equation of the least squares regression line and be sure to identify any variables that you use. Okay, now remember this was an indication of our power model. This is when we transform both the x and the y. So this is our predicted y here, natural log of the period would equal, okay, remember here's our constant, this is our y-intercept, 0.0002544 plus, okay, right here is going to give us our slope, and specifically this variable right here is actually the explanatory variable that we're using. So our slope, 1.49986, and that is multiplied by natural log of the distance, the astronomical units. Okay, this would be our equation for our least squares regression line. Now moving down to part C, it says use that model from part B, okay, to predict the period of revolution for Eris. Okay, now the period for Eris, which is illustrated by this calculation here, is roughly 102.15 astronomical units. So we're using that number to plug in as the distance from the sun. Okay, so it's asked us to show our work here. So we're trying to solve this for the period. Okay, the period here. So we're going to go ahead and plug the number they gave us for the astronomical units here. 102.15 is going to go in for the distance. Okay, we're going to type all this right side into the calculator. That's going to make the number on the right side 6.939. Okay, now keep in mind we need to solve this for just period, not natural log of period. So remember, natural log is a log with a base e, and so I'm going to raise so that the left side is the exponent on e and do the same thing to the right. That's going to cancel out the natural log, leaving me with just what the predicted period would be, and that gives us an answer of roughly, I'm going to make this approximately, 1,032 Earth years. Okay, that's how long it takes for that planet, Eris, to make one complete revolution there. Okay. All right, let's go ahead and take a look here at the next page. Now, this is piggybacking a little bit on what we just did here. So I have this written here. The prediction in part C, when we were asked to plug in the 102.15 astronomical units, our prediction was 1,032 Earth years. That's what we just wrote down. Now, here's what Part D is asking. Here you can see on the left, this is a residual plot for the linear regression that we did in Part B. Do you expect your prediction from Part C? Here's our prediction. They gave us this. We're predicting that would take 1,032 Earth years for one full rotation. Do we think this prediction is too high, too low, or about right? And we want to justify our answer. So here's what I'd like you to look at in this residual plot. Can you kind of see how these values on the left side are sort of curving down a little bit, and then here we are curving up just slightly here, okay? Now, Eris's value for natural log of the distance, if we were to substitute this given astronomical units right in here, okay, that value is 4.626. Okay. Do you notice that there is a little bit of a pattern here where it feels like over here on the right side, these residuals are more positive. Like if we kept with this pattern, 4.6, this is what the natural log of the distance is. Okay, that's why we were using natural log of the distance, because this is what our explanatory variable is. Okay, we make that substitution 4.46. So we're just going to say like, oh, that's going to be like somewhere right about here on our x-axis, and if the pattern continues, we might expect that point to maybe roughly be somewhere right about there. It feels like maybe it would fall on the far right side of this residual graph, and on the right side of this is feeling like where the residuals are kind of trending, where they're positive. Now remember the formula for residual. It's residual equals AP, actual minus predicted. Okay, now a positive residual, think about this, if this value is positive, it means the actual value was larger than what was predicted. So since the residual is probably going to be positive, that means that your prediction is likely a little bit too low. Okay, it's a little bit smaller than what we would expect. And so the question was, is it going to be too low, too high, or about the same? We would suggest that it's probably going to be a little bit too low. Remember, when you run these lines of best fit, again, residual is actual minus predicted. Any points, actual points that are above the line, okay, that gives you this residual here. Okay, any points below the line, the residual is how far off you are from your prediction. So points above the line, your prediction is below what actually happened. Any points, actual points below the line, now your prediction is higher than what actually happened here. Okay. All right, just kind of wrapping this up here, it says, what if a scatter plot for either doing log of both or only log of the y, what if both of those scatter plots actually look linear? Okay, because we're supposed to try to pick the one that looks linear, and then that kind of leads us to what that original scatter plot was, exponential or power. It says what you would want to do is you would want to fit a least squares regression line to both sets of transformed data, and then you would want to compare their residual plots. And here's what you're looking for. You're going to look for the one that has the most random scatter, the one that does not have an evident pattern. And if for some reason the two residual plots would look roughly the same, then you would want to use the standard deviation of the residuals. We would want that to be the smallest one, would be the better fit, or the coefficient of determination, the one that has like the most percentage of variation attributed to that explanatory variable. So here's how this would work. What you would do with the data set is you would put the original set of data, okay, the original explanatory variable should go into L1 on your calculator, and the original response variable would go into L2. So that if you made a scatter plot, okay, your scatter plot for this, the original data would just be a scatter plot of L1 and L2. Okay, it's very likely that you're going to see some type of a curve when you look at that original scatter plot, which is going to lead you to needing to do both of the transformations, the one for power and the one for exponential, and then kind of examine those two scatter plots to see which one appears more linear. Okay, now here's how you can do this on your calculator pretty easily. You're going to want to define L3 to be log of L1, okay? Log of L1. This is us taking the logarithm of the explanatory variable, and then you want to define L4 to be log of L2. Okay, now, this means that we just transformed the data, and if you're going to want to check to see if it's a power model fit, then you would make a scatter plot of L1 and L2. And by making a scatter plot of L1 and L2, what you're doing is you're checking for that power model, if that's a good fit. The other option is to take the transformed data set to check for an exponential model, which is where you leave the explanatory variable the same. So L1 is what you're going to keep as your x value, but you're going to pair that up with only log of the response variable, L4. Okay, and that would give you this. And then you would make a scatter plot of that to check and see if that comes out roughly linear. That means the initial scatter plot was exponential in nature. Okay, now, without necessarily doing this, we're going to take a look at this last example on the next page. It says, one sad fact about life is that we'll all die someday. Many adults plan ahead for their eventual passing by purchasing life insurance, and many different types of life insurance policies are available. Some provide coverage throughout an individual's life, that's called a whole life policy, while others last only for a specified number of years, that's called a term life policy. The policyholder makes regular payments, these are called premiums, to the insurance company in return for the coverage. When the insured person dies, a payment is made to the designated family members or other beneficiaries. How do insurance companies decide how much to charge for life insurance? Well, they rely on a staff of highly trained actuaries. These are people with expertise in probability, statistics, and advanced mathematics to establish what these premium payments should be. So for an individual who wants to buy life insurance, the premium will depend on the type and amount of the policy, as well as on lots of personal characteristics like age, their sex, their health status. The table shows monthly premiums for a 10-year term life insurance policy that is worth $1 million. So you can see here is the age of these individuals, and this is how much they would have to pay per month to be covered for $1 million worth of life insurance. Now, what you would do if you were actually doing this on your calculator is you would enter these ages into L1, you would enter these monthly premiums into L2, and L3 you would define this as either log or natural log of L1. Okay, and then L4, you would define that as natural log of L2. Okay, and it would fill in these columns here for you. Okay, and then you would make each of these 3 scatter plots. What you see pictured here on the left is nothing more than just the original data set, that is the scatter plot of L1 and L2. You can tell by looking at this scatter plot, there is definitely a distinct curve here. If you were just to run a regression with that, this is the residual plot that you would get. This is a horrible, horrible scatter plot to be running a linear regression with. Okay, so let's go ahead and try to transform the data. What we would then do is we would make a scatter plot of L3 and L4. That would be the scatter plot that you see here. Definitely looks much more linear. This is indicating that maybe that original scatter plot was in fact a power model. Okay, now it does look though that I'm seeing some type of a little bit of a pattern possibly here in the residual plot. I don't like that. Normally residual plots should show very random scatter in order to indicate that a linear regression really was a good regression to run. So let's look at our last option. Our last option would be to run a scatter plot with L1 and L4. That is the original explanatory variable paired up with the natural log of our response variable. Now here, again, feels like, ooh, okay, now these are also looking pretty linear. In fact, both of these transformed data sets looked pretty linear, but I really like how the residual plot looks on this last one. This is giving us some very nice random scatter as opposed to this one here that has a little bit more of a pattern involved to it. So if I had to choose which model I really thought that the original data set was, I would choose, based on the transformation that took place here, I only transformed the response variable. This is going to probably clue me in that it is very likely that the original data set was actually exponential in nature. Okay, what number 1 is asking you to do is they wanted you to use each of these 3 regression equations that you have underneath each of these to essentially predict what the premium payment would be for a 58-year-old who would pay for each of these policies in each of these 3 regression scenarios. Now, I'm not going to show the steps for this, but I'll go ahead for option number 1. The premium would be $157.54. For option number 2, the premium would be $141.30, and then the best one that we really should be using for these predictions is actually this last one, $136.89. So that brings us to the very last part here. It wants to know what type of function, linear, power, or exponential, is really the best to describe the relationship between that original scatter plot age and monthly premium, and we kind of already alluded to this, that an exponential model is the most appropriate because the scatter plot of, and here's my transformation, age and natural log of premium is the most linear. Now, they both actually kind of look linear, both transformations. So I want to add this in, and its residual plot shows the most random scatter. Okay, shows the most random scatter there. Okay, that brings this section to a close. I think there's just a few problems for you to go ahead and try that wraps up this section, wraps up the book, and that's a wrap on AP Stats.